Today, we are cracking open a materials science mystery that could totally change the car you drive. We're talking about magnesium, a metal that's packed with promise, but for decades has been a real puzzle for engineers. Let's get right into it. 30%. Just keep that number in your head, because it's the key to this whole story. That's how much lighter magnesium is than the aluminum we use in so many car parts today. I mean, think about that. Slashing the weight of a car by nearly a third, the change in fuel efficiency would be absolutely massive. So that brings us to the big question, right? If magnesium is this amazing, super light material, why aren't our cars already built with it? Why hasn't it just taken over the industry? Well, the answer has been this huge roadblock for automakers for years. To really get why, we have to dig into what I'm calling the magnesium conundrum. It's this fundamental trade-off that's kept this incredible metal stuck on the sidelines. Okay, so here's the heart of the issue. On one side, you've got aluminum. Sure, it's heavier, but it's reliable, it's strong, and most importantly, it's predictable. Engineers know exactly how it's going to bend and deform. Then you've got magnesium. It's got that incredible 30% weight advantage, but it's always been a bit of a wild card, unpredictable. And sometimes it gets brittle and just feels without warning. Now, this unpredictability, it's not some random flaw. It's actually built into the metal's architecture, right down at the atomic level. It all comes down to its crystalline structure. You know, the super specific, repeating way its atoms are all arranged. This internal blueprint is what gives any metal all its properties, its strength, its flexibility, the whole shebang. And here is magnesium's big issue. You see, in steel or aluminum, the atoms can kind of slip and slide past each other in all sorts of directions. That's what lets the metal stretch and bend so gracefully under pressure. But magnesium's atoms, they're way more rigid. They can only slip along these very specific pathways. So if you pull it or push it in a direction it doesn't like, it can't really stretch. Instead, it can just break. And that's the last thing you want happening in a critical car part. So, for decades, that was the puzzle. And to solve it, a team of researchers figured they had to do something radical. They needed to literally see what was happening inside solid metal as it was happening. And their approach gave us a totally revolutionary way of looking at this problem. And this was no small-time operation. We're talking about researchers from the University of Michigan with funding from the U.S. Department of Energy who had to travel all the way to France to the European synchrotron, one of the most advanced science facilities in the world. And they used this incredibly specialized technique called dark field X-ray microscopy. So what is a synchrotron? Honestly, the best way to think about it is like the world's most powerful magnifying glass. It whips particles around to nearly the speed of light, and in doing so, it generates these unbelievably bright, focused X-rays. These X-rays are so powerful they can literally see through solid metal and show us its internal structure in unbelievable 3D detail. The team's experiment was just so meticulous. They took a little sample of a magnesium alloy and started putting it under pressure. They'd apply a little bit of stress, then zap it with the synchrotron to capture a 3D image. Then they'd crank up the stress, take another picture, and then do it again and again, essentially creating a stop-motion movie of what happens deep inside the crystals as the load gets heavier and heavier. And what they finally saw? Well, it solved the whole mystery. They got a front-row seat to a phenomenon that scientists knew had to be happening, but no one had ever actually seen form in 3D before. It was a huge moment. They were literally watching the birth of what are called deformation twins. You see, when magnesium can't slip the way it wants to, it has a backup plan. It creates these tiny, perfect, mirror image copies of its own crystal structure inside itself. It's the metal's clever way of reorienting its atoms to handle the stress so it can deform without just snapping. The researchers came up with a really brilliant analogy for this. Think about a stiff piece of paper. If you try to squish it, it doesn't just crumple randomly. Instead, it might form these neat little accordion folds that let it change its shape. Well, deformation twins are basically the atomic version of those accordion folds. It's the metal bending without breaking. Sang-Won Lee, the study's lead author, put it perfectly. He said, "We literally watched the twin appear and evolve with our own eyes for the first time." You can just feel the excitement in that statement.
They weren't just looking at a before and an after picture anymore. They were seeing the whole movie. This was the key.
So what did they learn from watching this movie? This is the crucial part. They found two incredibly consistent patterns. First, every single one of these deformation twins formed at a very specific spot called a triple junction. It's a point where three of the metal's tiny crystals all meet up. And second, the defects, the actual points of failure, always, and I mean always, appeared right where these new twins touch the edges of other crystals. Suddenly, it wasn't random anymore.
And that discovery, that changes everything. It takes magnesium out of the world of mystery and puts it firmly into the world of engineering. This is how we start designing the materials of tomorrow.
Because now it's not a mystery, it's a blueprint. Once you know exactly where and how the weak points form, you can start to engineer alloys that stop them from forming in the first place. You can start tweaking the size and shape of the crystals to control where the twins pop up, making the whole material stronger and, most importantly, way more reliable.
So you can see the whole path laid out, right? We started with a problem, a super strong but totally unpredictable metal. Then came the breakthrough, seeing these twins form in 3D for the very first time. That gave us the blueprint, showing us exactly where things go wrong. And that blueprint is the key to the future, designing optimized, reliable alloys. And the science isn't stopping. The next step is to capture this whole thing, not just in stop motion, but as a true real-time video.
So, what's the big takeaway here? It's that by using the world's most powerful X-rays to peer deep inside a tiny piece of metal, scientists have finally found the key to unlock magnesium's massive potential. This isn't just cool science, this is the real foundation for building those lighter, stronger, and way more fuel-efficient cars we've all been hearing about for years. And that leaves us with one last thought. The fundamental science of why magnesium was so unpredictable, that's basically solved now. The next mountain to climb is all engineering and manufacturing. So the question isn't if we can use this incredible metal anymore, it's when is all this science finally going to show up in your driveway?